Okay, so good morning, everyone. Now that I can't see anyone, that's much better with these lights. So welcome to my talk about kernel development with modern C++. I didn't make any thorough check, but I think there was never a kernel talk at NDC anywhere, anytime. So that's a record. I actually was very surprised that the talk was accepted. And so kind of weird being here talking about kernel, but I see a few people, so we'll see how many of you will be left at the end of the talk. Okay, so my name is Pavel. I'm a developer, I'm a trainer, I'm an author, and apparently a speaker. And so I've written a few books. The latest one is about Windows kernel development. And so some of the stuff I'll describe today is actually some of the things I've done as part of my kernel development. I like to write in kernel mode. I like user mode as well. User mode is perfectly fine. But kernel has kind of its special thing, special power, and maybe special aura, maybe. And so I've written some other books. So again, as always, go ahead and buy them. That's very good for me. So go ahead and do that. I have several open source tools on GitHub and a few blogs you might want to read. So what is it about? What we're going to talk about in this session? So the idea is that in kernel classic development, drivers or kernel drivers were always written in C. And so this is kind of the hardcore, this is how low-level code should look like. C is the real language. Everything else is just those layers of abstractions that probably hurt performance and more memory allocations and who knows what. So you should always use C, and if you're really one of those brave souls, assembly language is really the best. But as a compromise, you can use C. And I'm talking from experience in the Windows and Microsoft space. And so if you look at the samples for drivers that Microsoft provides on GitHub, they're all written in C, even today. But in fact, you can use C++, and it actually can help create drivers that are more robust. Because as I'll describe shortly, in kernel mode, you're less likely to be forgiven for mistakes. One of the fatal mistakes that everybody knows about in Windows is that blue screen of death that everybody likes. And so this blue screen happens when there's an exception in kernel mode that is unhandled. In user mode, well, the process crashes, you can continue moving on. In kernel mode, everything crashes. And so you have to be extra careful in the kernel. And so using C++, this as I try to demonstrate, can actually make your code more robust, less likely to crash, and less likely to leak resources. And so I'm going to show you some examples. Of course, this is not a crash course in writing kernel drivers. If you are expecting to write kernel drivers after this talk, you'll be disappointed for sure. But just to give you some ideas of what you can do and how to think about these things to create more robust code, which of course is good for other low-level code, maybe embedded code, not necessarily something running in the kernel. And so classically, Microsoft didn't support C++ at all for kernel development officially until 2012. Up until then, you had to use C if you wanted to get any support from Microsoft. So people actually did use lightweight C++, like the ability to declare variable anywhere, not just the beginning of scopes. So this was actually fixed in C99, but Microsoft compiler didn't support that, so you actually had to declare everything up front. But it was unsupported, so you couldn't get official support from Microsoft if you had any issues for whatever reason unrelated to C++. But starting with 2012, Microsoft actually decided they're going to support developing with C++, and the compiler compiling your code is the same compiler that is bundled today with Visual Studio. And again, that wasn't the case previously. You had a different compiler for drivers and different compiler for user mode, which was kind of silly. They're all C++ compilers. Why should they actually be different? But now, thankfully, it's supported officially. But still, as I mentioned, the samples that Microsoft provides, some of these samples are the actual code of some drivers that are in Windows are still written in pure C, which I think is a shame. The kernel, by the way, in Windows is written mostly in C, but there is actually one piece which uses C++, and it always makes me kind of laugh a little bit, because there's one process that you will not see in Task Manager. It's called memory compression. Memory compression is a process that's available starting with Windows 10, the RS1 version 60.07, the anniversary update, where Windows actually can compress physical memory to conserve space. Now, Task Manager, if you open that and look for memory compression, it's not there, because there's a specific code in Task Manager that says if it's that memory compression, let's just continue and not show it. Why? Because people may see the memory compression process consuming lots of memory. They will say, hey, what's that junk? I mean, who is consuming .memory? But in fact, this is compressed memory, so it's actually saving memory. But people don't realize that with casual looks. So if you go ahead and look at the memory tab, for instance, you can see that currently on my machine there's 10.8 gigabytes of RAM used, but I have 595 megabytes, which is compressed memory, which means that I'm saving memory. Maybe the uncompressed memory is 1 gigabyte, and I'm only consuming 595 megabytes, so it's a good thing. However, if you look at different tools such as Process Explorer does not hide anything, and here you can find the memory compression process. It does exist, and you can see that its consumption is actually the same as the number of megabytes we've seen earlier. If you go ahead and double-click that and look at the Threads tab, you'll see code here that is part of NTOS kernel, which is the Windows kernel. And you can see it's C++. Not just C++, but it uses templates. I actually saw this source code in person when I was working for Microsoft for a brief period, and I was actually amazed that the store manager, which is the component that's managing the memory compression infrastructure, is actually written in C++ and uses templates. The rest of the kernel uses pure C. No C++ at all, and certainly not templates. So someone there, and I actually know who, did that. So kind of impressive, but their own drivers are still using pure C. Okay, so what's different about user mode versus kernel mode development? What's really different? I mean, why should we do anything different in kernel mode than we're doing in user mode? And so first, there was the thing I mentioned earlier about unhandled exceptions. If you have an exception and it's not handled in user mode, then that particular process crashes. So it's probably not very pretty, but it's not too bad either. Your system is intact. You can just go about your business. Maybe you had some bug, and you can correct that. Everything is good. However, in kernel mode, any bug is causing the system to crash with that blue screen. By the way, the blue screen is not Microsoft's punishment on developers. It's not that. It's really a mechanism to protect the system, because kernel code is trusted, or supposed to be trusted, because it's all powerful. You can do anything. You can actually make some damage that will prevent Windows from restarting. And so the purpose of the blue screen is to stop right now, so that any further code will not be able to cause any potential damage. And so you have to code very carefully in kernel mode, much more than in user mode. Another thing that is different is that in user mode, when a process terminates, for whatever reason, maybe normally, maybe because it was terminated forcefully, maybe because an unhandled exception happened, doesn't matter, the operating system cleans up everything. So all the private memory is freed, all the handles are closed, nothing is left. That is guaranteed in user mode. However, if you have a driver and you allocated some memory, for instance, and when the driver unloads, you forgot for whatever reason to deallocate that memory, no one will do that for you. And so you leak memory until the next restart. So you may wonder, why is the kernel not kind of tracking all these memory allocations and just freeing them when the appropriate driver unloads? And so the reason is that it's simply too dangerous, because it may be the case that the driver left that memory on purpose because it's talking to another driver that is going to use that memory to do something else. And so if the kernel would release that memory, the other driver will access memory that is not there, and we're going to crash the system. So the kernel can't really take any chances, and that's why it's not tracking any memory allocations, and it will not free any memory automatically. And remember that in kernel space, all the drivers are in one address space. This is different than in user mode, where each process has its own address space and they don't mix. So it's very easy, theoretically, to communicate between two drivers because they're running in the same space. So again, you need to be careful not to leak anything, because otherwise this leak will only be resolved in the next boot. Now what about return values from functions? So if you're calling Windows APIs in user mode, they return some value telling you whether you succeeded or not, and some developers say, hey, well, I'm calling this function, it's a very low probability that it would ever fail. They're not checking return values for every function. They're checking for return values for functions that seem to have maybe the chance, at least they see it, to fail. But in kernel mode, it's very, very important to always check for errors. You cannot really miss anything, because anything can happen. Even if you're trying to allocate, let's say, 10 bytes, which seems like a very small amount of memory, you can't really take the chance, because this could fail. Maybe the system is now very low on resources. The driver is in a system that it doesn't control. So anything can happen. You should always check for return values from functions or various APIs. There's something called the interrupt request level, which we don't have time to talk in detail. This is a term that if you have been doing any user mode development, you've never heard of. That's completely fine, because in user mode, the value of IRQL is always 0 for all processors, and so there's no point in introducing a new term when it's never changing and it doesn't affect you. But in kernel mode, the IRQL can be higher, and when IRQL goes to the value of 2 or higher, this puts some constraints on the way, on the things that you can do in the kernel. So in IRQL 2, you actually get to use memory which must be resident in RAM. If the memory is paged out for whatever reason, you're going to blue screen the system. You cannot wait for kernel objects. There's no way to wait, because the scheduler is asleep and cannot wake on that particular processor. So there's some very strict limitations on this type of code, and so you again have to be extra careful. So generally, if you have some bad coding from whatever reason, they're more likely to be affecting the entire system when you have a driver, because a driver typically services many processes. And if the driver deadlocks or something like that, it could deadlock many processes. And so again, you have to be extra careful. When you're testing or debugging user mode applications, you just attach your debugger to a process and then just debug it. Very simple. On your developer machine, everything is nice and cozy. In kernel mode, you can't really do that. If you want to debug a driver, you have to debug a different machine. It could be a virtual machine, but it must be a different machine. And so when you set a breakpoint, you actually freeze the entire machine. There's no way to debug a particular process on the other machine. You debug a machine. And so the debugging is more complex and more time consuming. And that's why you probably don't want that many bugs in your driver, because it just makes everything take longer. So what about the various libraries that you know and perhaps love? So in user mode, you can use any C++ or C library under the sun that you can find. In kernel mode, you can't use them. You can't use most of them, if not all, and I'll show you why in the next few slides. Exceptions. So in C++, in classical C++, you can use throw statements to throw exceptions. You can catch them with try catch and all these things, but you can't do any of that in the kernel, because in the kernel there is no C++ runtime. There is no C++ runtime, and that has several implications. One of them that you cannot use the classic exception handlers. And so Microsoft provides its own mechanism for exception handling. This is part of the kernel called structured exception handling, which is also available in user mode, by the way. And so if you want to take advantage of exception handling, you actually have to use some extensions to the C language to get yourself those proper keywords to be able to catch exceptions. But of course, these are not high-level exceptions. These are not objects that are being thrown. These are just numerical values with some parameters. So if you want to handle exceptions in kernel mode, SEH is your only option. There is nothing else. And so the bottom line is you don't have a runtime. So what does that mean? So for example, let's say you have global variables. And so global variables may have constructors. And so if you're working in user mode, when your main function starts to execute, all those global variables were already initialized. So someone had to call all the constructors. And this is in fact done by the C runtime. So the C runtime is actually the first thing relatively that user mode code that is running, and it's the one calling your constructors and then calling your main function. So there's something there. But in kernel mode, you don't have that. There is no C++ runtime, so no one is there to call your global object constructors, which really means you can't use them. So you can't use global objects that have constructors. Maybe you can just define a pointer and then allocate them dynamically. This is something you can do, and I will show you how to do that. But you still have to do some work because the new operator isn't supported as well. Because again, this is part of the C++ runtime, and new doesn't have any implementation in a kernel. But because you can overload that, you can fix that. Okay, so this is kind of some of the constraints that we have in the kernel. So there's no runtime. And that means I have to take care of some things that will not be taken care of otherwise. However, most of the C++ features that you know actually work just fine in the kernel because they're just compiler mechanisms. So stuff like auto, lambda functions, range-based force, templates work just fine. As we've seen, the kernel itself is using templates, so they must be working. You can have move semantics, you can overload operators. So everything normally available to the C++ developer from the language itself is available. So anything that is not dependent on a runtime works just fine. You just can simply use it. So just to kind of make this more concrete, we're working in that yellow box at the top. That's the kernel space. On 64-bit systems, that's an address space of 128 terabytes. So of course, the kernel doesn't consume all that memory, otherwise it will not exist. But this is just a range of addresses that the kernel can use and drivers that are there can use. So they're kind of running together in that one big community called kernel space. Whereas processes, each one has its own potential 128 terabytes of memory. So communication between processes is more difficult because they have their own address spaces, but communication between drivers, for instance, is relatively simple because these addresses at the top are absolute. They look the same from whatever process you're looking at. Okay, so I want to start showing some code examples of how we can leverage C++ in the kernel to make our code more robust and less likely to leak or crash. And so the first thing is something that is definitely not new, something known as the RAI idiom in C++, or resource acquisition is initialization, which is a very bad name, but it is the name, so people typically use it. So this is the classic C++ cleanup mechanism, where you want to take something and then you want to make sure that something is released. And so in the kernel, I think it's even more important than in user mode, because if you leak something in user mode, when that process terminates eventually, everything is cleaned up. But in the kernel, that simply doesn't happen until the next restart. So it's very important to make sure you don't leak anything. And of course, some types of leaks can actually lead you to a deadlock. So let's see one example. So let's say I'm using locks. So I want to use something like a mutex because I need to protect some data structure from concurrent access. And so the classic pattern here says I need to lock some kind of mutex or acquire that mutex. So only one thread can acquire that mutex and then continue execution and accessing that shared data. All other threads trying to acquire the same mutex at the same time will wait, will go into a wait state without spending CPU cycles until that first thread finishes working with the data. It will release the mutex, and one other thread, just one, can acquire the mutex and go ahead and do its own work with the shared data. So this is the general idea, and we can generalize this further by using templates. So here I have a class called AutoLock. This is very similar to the LockGuard class in standard C++. And so actually I'm taking lots of ideas from the standard library that I know exists in user mode, which I can't use, and just re-implementing them, maybe with some semantic changes to fit my needs or my style, but I'm trying to get to something which is very similar. So you can see here I have this auto lock, and it's templatized on whatever lock I want to use, because there are several types of locks that are available in the kernel, and I don't want to create separate classes for different types of locks. And so I'm accepting this tlock template parameter and using that and storing reference to the lock. And we can see here that what I expect from that tlock structure is to have two functions, lock and unlock. So I don't care what that is, and I'm using that duck typing feature in C++ templates to just bind to the proper functions. And so here's one example of a mutex. So in fact, the classic mutex that you know from user mode is also available in kernel mode, but in kernel mode there is another special mutex that is not exported to user mode called the fast mutex, and it is a little bit faster. So one sense in which it's faster is because it doesn't have ownership, and so it doesn't know which thread acquired it, which means you can't acquire that recursively, which you can do with the classic Win32 API mutex. And so here's my mutex, and it has the lock and unlock functions, and that's good enough. So here's an implementation of that mutex. I'm using kernel APIs to initialize the mutex just once, and then lock is going to call the xacquire fast mutex function. This is the function in the kernel that does the acquisition, and then release that same mutex in the unlock function. And now if I want to use it, it's very simple. Whenever I need to acquire the mutex, I can open even an artificial scope if I wanted to just limit the mutex handling just to the smallest scope I can handle. I'm just acquiring that and then doing whatever needs to be done. If you're using C++ 17, which is fully supported, by the way, you can remove that class name, because C++ 17 allows you to kind of infer the type of template parameter based on the parameter to the constructor, the myMutex thing. So this was added in C++ 17. And so this is one example. And there are many other examples, and everything I'm trying to do in the kernel that has this acquire and release semantics, maybe it's about threading, maybe it's about locks, maybe it's about memory, doesn't matter. I'm trying to create these RAI wrapper classes. So here's another example about handles. So handles is something which is very common in user mode and in kernel mode. And in fact, I use a very similar class in my user mode development as well. Because once you get a handle to whatever kernel object you're working with, maybe handle to a file, handle to a mutex, handle to a semaphore, to a process, whatever, you need to close that handle as soon as you don't need it. And again, if you don't close the handle, you leak the handle. And this is, again, eventually it manifests itself as just using more memory. And in user mode, so worst thing, when the process terminates, then that handle will be closed. But in kernel mode, it will not. And so I can create a class called the generic handle, which accepts a handle for with whatever type of handle I'm using. There are maybe several types of handles around. And there's a traits class. This is one of the ways to implement this idea, and that traits class is really holding a set of static functions that do some specific things, such as giving me back what an invalid handle means for this particular type of handle. And I need to close the handle. I'm going to call a function called close on that traits object. So if I have a handle of one type, maybe it has one type of function that closes that. Maybe for a different type of handle, there's a different closing function. And so I can kind of encapsulate that by a traits a traits class, which is provided here as an argument. And then I can create some concrete traits and handle classes. So for example, for classic kernel handles, this is going to be the traits. The handle type is handle, and so I have this close, is valid, and invalid handle functions that I can plug in for any handle that I need. And so I can even using here and say kernel handle is really generic handle with a type of handle and these types of traits. And I have other types of handles in a similar fashion related to, in this case, to file system mini filters. But again, the idea here is that I don't have to worry about releasing something. When it goes out of scope, it will simply be done. So destructors are called normally, no problem there. So Rai is a classical example, and of course you should use it in user mode just as in kernel mode. But kernel mode is kind of a little bit more important. So let's move on to memory allocations. And so in classic C++, we're using the new and delete operators. And as I mentioned, since we don't have any C++ runtime in a kernel, this simply will not compile. And so what can we do about it? And of course, the classical answer is let's override new and delete and provide our own implementation. And so in the kernel, the way you work with memory, at least one of the most common ways to work with that, is using the kernel pools. And so the kernel pools can be used to allocate memory using this main function, xAllocatePool with tag, which is very similar in concept to something like malloc. It says, how many bytes do you want to allocate? I will allocate that for you. But there are two other parameters here. One of them is the pool type. So in kernel mode, there are actually two main pool types. One of them is called non-page pool, and the other is called page pool. So non-page pool is a very special pool in the sense that everything you allocate there is actually going to be in RAM and will never be paged out. You don't have that power in user mode, but in kernel mode you have. And so if you need your data structure to be available, for example, to being able to access that in hierarchical 2 or higher, which I briefly mentioned earlier, you want to allocate that from non-page pool. In fact, if you open Task Manager again, you'll see here that we see here something says page pool and non-page pool. So it actually shows you how much memory is consumed right now in the two types of pools. So the page pool is sort of normal memory. So some of that memory is currently in RAM, some of that memory is paged out. However, the non-page pool means that 900 and something megabytes of memory is currently allocated from RAM, and it's not going anywhere. So it's not going to be paged out any time until the driver that's responsible, or the kernel itself responsible for that, those allocations will start freeing allocations. And so as opposed to malloc, I need to provide some information onto which pool I want to make that allocation from. And then the last parameter here, which actually is somewhat optional, is called the tag. And the idea of a tag is to mark my allocations. And so I mentioned that if I allocate memory and I forget to free that when the driver unloads, nobody's going to free that. So how can I know if my driver leaks memory or not? So one classic way of doing that, it's not actually another better way to do that today, but the classic way is to tag my allocations with a 4-byte value comprised of ASCII characters, and then open some tool to show me whether these characters appear in the list of pool allocations after my driver unloads. So if I don't find my tag, I know I'm fine. I've released all memory. If I find my tag, then obviously I haven't released all the memory. And so there are several tools. The classic tool is Poolmon, which is a console-based tool. I hate it. And so I wrote my own version of kernel pool monitor. So I actually wrote two versions. I'm going to show you the second one. And this actually lists all the tags that are currently used by the pool. And each one of these tags, we can see information about how many allocations have been done, what's the current consumption of page or non-page pool, and this is updated dynamically all the time. We can also see some information here in the source and source description to understand from which component this actually comes from. And so we can see many of these allocations are coming from Windows itself. So you can see here NTIO, for instance. This means this is the I/O system or the I/O manager as part of the kernel. And so what a typical driver does, it tags its allocation with these up to 4 ASCII characters to distinguish itself from all other drivers and kernel components. And then it can also look, while the driver is running, what's going on with the allocations that the driver has been using. How much memory is he consuming, how many allocations, how many frees. So this is all tracked, and we can use such a tool to look at that. And of course, this is available also when you're working with a kernel debugger. And so what I want to do is make sure that I call xallocate pool, and then I call xFree pool whenever that's needed, and I don't forget that. So I need something that allows me to kind of do that properly. So one thing is maybe creating some wrapper. But first, I don't really want to call these functions, because maybe I want to allocate memory for my own structure that has a constructor. And if it has a constructor, if I just call xallocate pool with tag with the size of my structure, the constructor will not be called. And so I want to do something to make it work. And so the first option is simply to overload the new and delete operators. So we know that the new operator can be overloaded, and the first parameter must be a size t, but I can actually add more parameters, as many as I want. This is not a new feature. This has been available in C++, even in the C++ 98 standard. And so because I need the pool type and I need the tag, I want to provide these as part of my definition of the new operator. And I can, of course, define and delete in similar manner. So here's an example implementation. So what I'm doing here, I'm calling xallocate pool if I don't have any specific tag, because then the kernel will provide a default tag, or xallocate pool with tag if the tag is not 0. And if I fail for whatever reason, I'm just issuing an output to the debugger if it's attached, and returning that pointer. So this is all I really have to do, because as part of operator new, calling the constructor is part of the code the compiler will inject automatically. So I just need to provide the compiler with a way to actually allocate the memory. The calling to the constructor is going to be done automatically by code injected by the compiler. So that simply works. And then all I need to do now is simply create my own data structure, whatever that may be. So here's a my data structure that may contain sub-objects that may themselves have constructors, which is definitely possible. And I'm showing a vector here, which I'll discuss in a moment, and just doing a new operator that looks like this. So this is, again, this syntax is not new. It always was available in C++. So new something, the something is my data, but all the extra parameters, except for the size, I have to provide with parentheses before the actual type. So in this case, I'm saying I want to allocate a my data object from non-page pool, and I have some define for driver tag that I provided earlier in the code. So that would be one way of working with that. Another way I can use memory allocations in this case is using something which, again, is not new, called PlacementNew. PlacementNew is the idea that says the memory is already allocated. Some entity allocated a chunk of memory for my object, but that entity has no idea what's the purpose of that block, so it's just a set of bytes. So what I want to tell to the operator new, just call the constructor, please. This is all I want. The memory is already there. So this is exactly the point of PlacementNew. So PlacementNew looks like this, and the implementation is trivial, because I'm accepting to the PlacementNew the existing pointer where the memory has already been allocated. All I need to do is just say, OK, that's actually here. And again, the benefit here is the compiler will add a constructor call. So I'm going to do a new, which actually allocates nothing because the memory is already allocated, but the constructor will be called right now. And so how do I call the destructor in this case? But here's the call to the new operator. And so in this case, I'm calling xAllocatePool with tag explicitly, but let's suppose I get a pointer from some Windows API, some kernel API that already allocated some memory for me. Or maybe some other component, I have no idea how it allocated the memory, perhaps. But it is allocated nonetheless. And so now I just want to call the constructor to initialize my object properly. So I'm doing new with the pointer and my data. Notice I'm not even bothering capturing the result, because the result of that new will be data itself. So writing data equals new data, my data is really useless. I'm just using new data because the pointer will not change. This is exactly what PlacementNew returns, the existing pointer. And so from the perspective of releasing the memory, I need to call the destructor now explicitly. And so the only way I can do that is by invoking the destructor explicitly using the pointer itself. This is, again, this syntax is supported in C++ because there's no other way to do that. Because I cannot call delete here because it was not allocated by new. It was allocated by something else. And so I have to call the destructor and then deallocate the memory explicitly using the same function that deallocated the memory, maybe some library function that I'm calling now. But this is the way I have to work in order to actually invoke the destructor. So once I have this kind of code in place, I can go ahead and use new, delete, or this kind of code if I have to. So what else? What about strings? Now, strings are always fun. No matter what library you're using, user mode or kernel mode, these libraries tend to always invent new string types. Have you noticed that? That every library you're using, there's a new string type. Everyone's saying, oh, all the other strings are garbage. I want to write my own string type. It's going to be better. And that's kind of always boggles the mind. There are so many strings out there in user mode. And so the kernel, of course, has to have its own string type. And the way strings work in the Windows kernel, most of them, is using a structure called Unicode string, which has members to one member is just pointing to an array of characters, and there are two members saying what's the length of that string. And to make things a little bit harder, the length is in bytes, not in characters, because Unicode here really means UTF-16. So we have 2 bytes per character. So the length is actually in bytes, not in characters, which actually kind of confuses some people. And there's a maximum length that indicates how much that string can grow without doing any special reallocation. And of course, this is just a structure. This is a C structure. It has no special management. If you try to append to that string something that causes the length to be more than the maximum length, you're screwed. So you're going to probably blue screen the system. So you have to reallocate everything yourself. And so the first intuition in this case is saying, well, maybe I should create a class that would wrap Unicode string. And that looks like a good idea, but in practice it doesn't really work that well, because this Unicode string, the buffer itself, the pointer to the buffer, is not necessarily owned by that string. Maybe that pointer came from somewhere else and that string just describes that buffer. And so creating a class, I tried that actually, that wraps a Unicode string, made that class almost useless. So I couldn't use it in any good scenarios, at least not without getting confused when it's owning the pointer, when it doesn't own the pointer. It kind of looked bad. So I decided to go another way and do what everybody else does, create my own string type. I mean, everybody's doing it, I can do it as well. And so I can create a string type. So this is always fun. I mean, you kind of going back to your C++ basics, where you create a string type with a pointer to something and maybe a length, and then you create all those operators and kind of, I think it's fun sometimes to go back to the basics, and now you can do whatever you want because you're not constrained by any library. You don't have to create your string to be exactly like std string in user mode, stdw string. You can do anything. You can do whatever pleases you, and you can provide the API that you think is more intuitive for whatever you're doing, because this is essentially just for you. So just for fun, I created here a class called KString, and this class accepts a tag and a pool type, again, because I'm going to allocate dynamically a set of characters, and so I need to select the appropriate pool. So we can provide these parameters as part of a template or maybe part of a constructor. So again, this is a trade-off. This is a design decision that you can do. And then you can have various constructors and operators and copy constructors and move constructors and whatever you need. And to make it easier to work with Unicode strings, I have a function here that allows me to expose that KString as a Unicode string using this getUnicodeString function. And so if I have this function, I'm accepting Unicode string pointer from wherever. I'm simply filling in, this is one way of doing that, initializing the members in that Unicode string to point to my internal string that I'm managing. And so that Unicode string is not going to be the owner of the string. I'm continuing to own that string, but any API that needs Unicode string, I can provide that. And so this really made my life easier when working with strings, because I have a simple string class. It supports operators and all the other things that strings typically support. And anytime I need to call an API in the kernel that wants Unicode string, it's very easy to get one without getting into trouble related to ownership things. And of course, you can go ahead and do these things for other types, such as a vector. So a vector is, again, a very, very popular type in user mode, std vector. Everybody's using that, and for good reason, because it's contiguous in memory. It's very fast. And so maybe I need these things in kernel mode as well. So I did that. I created a class called kvector, again, templatized with the pool type and tag and so on, and provided my own operators for adding items to the vector, removing, and so on. And so you have kind of the chance here to reinvent a minimum standard library for your work, because there's nothing you can use that is available. You can try to get ideas from existing libraries, of course, but of course you don't have to. You can do whatever you want. So let's look at another example where we can do something to ease our work in the kernel. And so the kernel uses one very common data structure to manage lists that can grow to any size using a linked list mechanism. And so there's a type called list entry, which is just a simple structure that has a pointer forward and a pointer backwards. So it's sort of the link in a linked list. And so this points to another object that has these pointers, and this points to another object, and so on. And as you can see in the diagram at the bottom, we have some head to the list, which is stored in some management structure, and then we simply provide this linked list to elements, and the actual list entry is the member inside that data. So this is one way of working with linked lists, and this is the way the kernel works with its own linked lists. And that API is completely documented, and so driver writers can use the same API. And so if you have a pointer to a list entry object, how do you get to the actual pointer to the real structure that you care about? And so you need to do some pointer arithmetic with the size and the offset of your entry inside that big structure. And so the kernel provides a macro called containing record that allows you to kind of take your pointer, your internal pointer to the actual list entry, and then get back the real pointer with proper casting to your data structure that you care about. And so this infrastructure already exists. But of course, these items, adding items, removing items, and so on, you have to use the API. So you can create a class to wrap these things in a nice way. So here's one example of how we can do that. So I can create a linked list, a data structure. And since in many cases a driver accepts requests for multiple processes at the same time, so it has to access these kinds of lists in a safe way, which means it has to use some lock. And so again, what I'm doing here is accepting a potential lock as a template parameter to the linked list. So I'm defaulting that to fast mutex because this is in practice the most common type that is used, but you can use some other types that are available, such as a spin lock and a normal mutex and some others. And so I want to have that lock as part of my structure, and then whenever I'm going to do any operation that changes the list, I'm going to acquire that lock, whatever that may be, using the same auto lock structure I've shown previously in the RAI example. So here's a few examples of how to implement these various functions. So here's my push back function accepting an item of type T. So that type T can be anything, but it must have a list entry field with the name entry. This is something I require for this code to compile. Otherwise, the duck typing of C++ templates will not work. And I'm calling here insert tail list function, which is a document kernel function, just utilizing that in an easier manner. So the client code would just say push back, here's my data pointer, and just do it. Same goes for a push front and some other operations I can have. It's very easy. If I need to get to an item, I can use the containing record macro here to do for me the offset calculations to get from the internal structure to the top level structure which I care about. So here's an example, at least supposed to be an example. And so the example creates a data structure. A machine decides that maybe freezing is better in this time. And so I have my own data structure. Let's call it my data. It can have anything, but one thing it must have is this list entry structure that must be named entry because my code relies on that. And so this will be the location where the forward link and backwards link are going to be stored. And once I have that, I can declare a linked list of type my data, call it whatever, and then just go ahead and create an instance of that my data after initializing my list, and then just call pushback, for instance. And so it's very easy to work with that, very similar to something like std linked list or std list. And so again, I have an opportunity here to create my own standard library that suits my needs. I'm not creating something for the entire world necessarily, but I'm creating something that I'm eventually going to pack in some library, and then I'll be able to use that in multiple projects, in multiple drivers. So just as we have standard libraries in C++ in user mode, I'm creating my own standard library and helpers in kernel mode for my own driver projects. Okay, so the last example I want to show you is using some more interesting features from C++ 11 and beyond, specifically templates or variadic templates. So variadic templates, I think, is one of the coolest features in C++. You can do really interesting stuff with variadic templates. And so I'm talking here about something called components. So what are actually components in this context? So a component is the class that implements various types of functionality. It supports several interfaces, perhaps. And when I get an interface pointer, I can work with the object with that particular functionality. And I can also ask the object, do you support a different type of functionality? And then if so, I'm going to get a different interface pointer to that particular functionality and work with that functionality. So if you have been doing any Windows development in user mode, you may have heard of something called the component object model, or COM. How many people have heard COM? Just raise of hands. How many people like COM? You can. Okay, 2 people. That's good. Usually, other people just okay. COM. I wish that was dead already, but COM didn't die and actually made a comeback in Windows 8 because the Windows runtime in Windows is based on enhanced version of COM. So COM is not going away anytime soon. So don't worry about it. However, COM may sound complex or may look complex because it has some complex parts, especially around threading models in apartments. When people hear that, they typically just want to jump out of the window. But the fundamentals of COM are very, very simple. It's about interface-based programming. That's the first principle of COM. And the second one is about location transparency. So I have no idea where the component is. Just get me this object with this class ID. This is what COM actually has. And And from this perspective, COM is a very good model. And so what if I want something like this in my kernel code? I want to create kernel components, and each one can support different types of functionality, and I want reference counting to be available because I don't want to track each reference. I'm maybe handing out these references or these pointers to multiple threads, and so I need reference counting to be available. And so if I think about the standard C++ library, I may think maybe I should create something like shared pointer. However, shared pointer does track reference counting, but it doesn't provide any support for this querying of functionality. And I certainly don't want to use something like dynamic cast and RTTI. I mean, that's terrible. I want something that will be completely at compile time. And so, again, if you're familiar with COM, Microsoft provides several ways of implementing or creating COM components using libraries such as the active template library and the Windows Runtime library. But however, I can't use them. I can't use them. In any case, I probably don't want to use them because they're ugly. At least ATL is very ugly because it was created many years ago when variadic templates didn't exist. And so the solution, let's create our own components. We can do it ourselves. So let me show you an example of how to do that. So I have this component, the basic interface for components. I'm going to call that iComponent. This is very similar to the IUnknown classic interface from classic COM, which provides two functionalities, really. The first one is querying for another interface for a different kind of functionality based on something called the interface ID. Now, in classic COM, this is a GUID, but really, because I'm not writing something for the entire world, I'm going to use IDs which are just simple numbers. I don't need to use real GUIDs, although I can. And the other thing is managing a reference count using these addRef and release functions. So addRef should increment the reference count, and release should decrement the reference count. And if the reference count is 0, the object should terminate itself. So this is a base interface. These are all pure virtual functions. And by the way, these annotations, like the in here and out PTR here, these are called syntax annotation language, or SAL annotations. And this is just a way for providing metadata over parameters. And it can be used by, so first, as a human user, I can understand that this is an in parameter, this is out, and some other stuff that is available in SAL. But also, static analysis tools can go over my code and see if I'm using properly variables as the SAL annotations indicate. So just to give you a brief idea of what that is. So this is iComponent. This is just an interface. And so what I want to be able to do is support reference counting and support querying of interfaces. So here's what I'm doing. I'm creating a class called component base, which is inheriting from multiple interfaces provided as variadic templates. And so I can have as many interfaces as I want. And this public interfaces ... actually inherits from all the interfaces provided as part of this component base. And so what I want to make sure is that there is at least one interface. Otherwise, the class is really useless. And so I'm using static assert here to make sure that the size of the interfaces, this is size of ... which is a special size of that works on parameter pack. Parameter pack is the term used for the variadic templates parameters. And so it must be greater than 0. Otherwise, I'm going to get a compile time error. So static assert is very useful, and you should use it because it's all in compile time if you can. And so what I have in my class here, the basic thing is I have just a reference count. So I need to manage that reference count. I need to manage that reference count in a thread-safe way. So here's addref. And so if you would try to implement something like this in C++ in user mode, you will probably use something like std atomic of int or something like that and do a ++, and that's it. However, we don't have atomic in the kernel. Again, the standard library is not available. So I'm calling the real function, or the real intrinsic behind the covers, called in Windows interlock increment, that allows us to do a thread safe ++ on whatever variable that we want. Same idea goes for release. I'm calling in interlock decrement, and then looking at the new reference count, And if it's 0, I'm going to just delete the specific object. Of course, that will only work if I have proper override for the delete operator. And of course, I'm assuming here that the object will be created by the appropriate new operator that complements this delete operator. And of course, I have to provide all that later on. But addref and release are fairly simple. So the most interesting function is actually query interface. So query interface says, hey, Mr. Component, here's an interface ID. Are you supporting that? If so, please give me back a pointer to that interface. If not, just tell me that you don't. And so this is something we need to do using variadic templates. Now, the trick in variadic templates, like all the ideas in compile time programming, is recursion. We're going to use recursion. And so we're saying we have a list of interfaces. Let's take the first one and see if it's supported. If not, let's remove that. Let's take the second one, and so on, until we're out of interfaces. So this is kind of the classic template meta-programming approach, which is required here. And so this is my query interface function that is provided by the iComponent interface, and I need to implement that. So I'm going to use a helper function called query interface, which is going to get this parameter pack of types. And so this query interface, which is shown here, is separating the interfaces to the first and the rest. So again, this is the recursive part. And so in this case, what I'm doing, I'm checking that particular interface ID. If it's the ID requested by the client, then that's great. I'm just returning static call, so that interface pointer to this, and providing the interface pointer back to the query interface function. If not, I'm calling myself recursively with the rest of the interfaces. So again, the now interface is going to be the next interface, and so on. And so like any good recursion, you have to stop it at some point. Otherwise, the compiler will go into a crazy loop and burn your machine. And so you have to provide some stopping mechanism. And the trick here is doing something like this, saying template. And I can't really use an empty brackets here that will not compile properly, because that would that actually means the compiler stands specialization, which is not the case. So this actually works properly. And this would be called when there's 0 interfaces. And so if I have no more interfaces, clearly I don't support it. So this would be my kind of stopping mechanism for the recursion. And then when we get back here from this query interface, we're going to get this result. If it's not null, I'm going to increment the reference count and return that pointer to the client with the status success. Otherwise, I'll just return status not found. And so this is the trick here. And remember, this recursion is only happening at compile time. So it's not a problem. It may take the compiler a few more milliseconds to actually do this thing, but I don't care. This code is generated at compile time, depending on the actual interfaces I'm requesting or using. So here's an example. Here's an example of 2 interfaces I created. iFilter and iProcessNotify mean whatever they mean. They all inherit from iComponent, my sort of unknown interface, and adding their own special functions. And then when I want to create my component that implements these interfaces, this is what it's going to look like. I'm going to create my class. It's called my filter here. And I'm going to inherit component base and a list of all the interfaces that I actually support. So the list can be as long or as short as I please, but I do have to have at least one interface, otherwise that static assert call will fail compilation. And then I can just implement this interface. In this case, I'm just having a shortcut here to create an instance of that class from outside using a static function. But typically, it will happen in another function or another class, which is typically known as a class factory, as it's implemented in classic COM. But I've kind of made some shortcut here just for demonstration purposes. And so now I can create an instance, and if I want to check for different functionality, I can use query interface. I want the iFilter here, and if it returns as not null, then this exists and I can use it. And of course, I have to make sure I call release at the end. And so naturally, I'm going to create a RI wrapper, which will be a smart pointer around interface pointers, which is very similar to what you have in user mode in class such as CCOM PTR that you have in the active template library, for instance. So again, you can do whatever you want, all work with templates, such as these variadic templates and meta programming with templates. Everything works as expected because these are just compile time mechanisms. And so the fact that eventually this code is going to be running in the kernel has no real consequence. I mean, it's just code, and the compiler does the right thing. And so with these ideas, I can actually create my own robust framework for working with the kernel. Don't have to continue working with C. My code is more robust because I don't leak anything, and I have higher abstraction mechanisms to do the things that I want to do. So once I have my string class and my vector class and my auto lock and all these things, I'm actually streamlining my work and don't really have to worry about these things and just need to worry about the actual functionality I want to provide to my driver. Don't want to worry about that infrastructure, which is a big headache when working with the kernel. You have to be careful. But now I don't have to be very careful. I already tested that. It works for me in one driver, then it probably work for the next driver as well. And so if you are planning to work in the kernel and you think, well, I have to go back to my C roots and just work with C all the time, then hopefully you see that there's another way. But you can take from this also other ideas that you can also implement in user mode, of course. All these things that I've shown you are mostly available in user mode as well. You don't have to perhaps overload new and delete most of the time. But of course, you can do that. You can have special type of requirement for memory allocations. So I'll be available later if you want to ask any questions because we are currently out of time. So thank you for your attention.